Gandhinagar, who will talk about a simple proof of the Wiener-Ikehara Tauberian Theorem.
Thank you, Alia. Thank you, everyone. So I'm very sorry to have missed out on the conference and missed out on all the fun, and I'm not being able to be there in person. But I'm really grateful that I'm getting an opportunity to speak online, and I'm thankful to the organizers for this. So, at the risk of running out of time for my talk, I just want to say a few words for Professor Murthy first. So, we all know about his mathematical legacy, and of course, I cannot express in words how much influence he has had on me mathematically. And it's very clear that I wouldn't be where I am today without his mentoring and his support. But I just want to say a few things about his the personal side of him as a mentor. So I remember, like, when I first came to Canada as a PhD student, this was in 2012. I was quite overwhelmed and bewildered, actually, and there was a lot of self-doubt about what I would be able to accomplish. And I remember that he was always very supportive, and his whole attitude has been like, to just go ahead and one should just do the math, enjoy it, and just do the best that one can do without getting too caught up in these routes and these questions. And that has actually stayed with me, and I think that has given me a lot of confidence. For example, I remember that there was this time that I was supposed to give my first sort of public seminar talk, math seminar, number theory seminar talk at Queen's. And I was very stressed. And I just, on the day of the talk, I just ran into his office without any appointment. And he was getting ready to have lunch. He was with his peanut butter sandwich. And I remember that he just welcomed me and he even offered me a banana. And he just heard me out calmly. And he was not, he was very welcoming and very calm. And just his presence that day, I think it calmed me down. It's another story that he can tell you that I put the banana peel in my bag and all that. But yeah, I remember that it just was very supportive of him to just listen to me and calm me down like that. So there are many such instances, but I just want to say that he has been a big pillar of strength in my life, and I wish him a very happy birthday. And I hope he had a very nice birthday conference, and I look forward to seeing him soon. All right, so I should start with the talk. So I'll be talking about some recent joint work with Professor Murthy and Jagannath Sahu. This is a simple proof of the Wiener-Ikehara Tauberian Theorem. So, So let's start with Abel's theorem, which says that we are talking about a real power series. If you have this information that the sum of its coefficients converges, then you can say something about the limit of this power series at the boundary of convergence. So if summation en converges, then this limit as x goes to 1 for the power series exists, and it equals this sum of these coefficients. So question is whether the converse is true. And one can see through a simple example that it's not. For example, if you take this power series, minus 1 raised to n, x raised to n, then at the boundary, it does converge. Okay, you get, as x goes towards 1 from the left, you get a 1/2 as the limit. But you can see that the sum of the coefficients does not converge. The partial sums of the coefficients does not converge. So Tauberian theorems originated with this, trying to answer this converse of Abel's theorem. Tauber showed that you can actually answer this converse conditionally. So you need some growth conditions on the coefficients. And if in particular, he showed that if ANs are little o of 1 by n, then you can actually answer this converse. So then the behavior if the series converges at the boundary, you can actually say the same thing about the sum of the coefficients of the power series. Now, we are more familiar with Tauberian theorems in the context of Dirichlet series. And in the context of Dirichlet series, they tell us something about the sum of the coefficients of the series, provided this Dirichlet series satisfies certain conditions. So this was done by Ikehara. This is called the Wiener-Ikehara Tauberian Theorem, dating back to 1931. So Ikehara was a student of Wiener, and using a result of Wiener, he proved this, that he obtained an asymptotic formula for partial sums of Dirichlet series satisfying certain conditions. So I will say what the theorem is. So let us just work for now with a series having non-negative coefficients. Okay, so this is our Dirichlet series, and it converges absolutely to the right of real part s equal to 1. And this is familiar to all of us. We also want that, we also have that it can be analytically continued to real part s greater than equal to 1, except for a simple pole at s equal to 1 with residue r. So, for example, this we just use it without thinking for the proof of the prime number theorem, for the where GS is the Riemann zeta function. Then what we can say about the sum of the coefficients is that this summatory function, summation bt, t going up to x, as asymptotic to rx as x goes to infinity. R here is the residue at that simple pole. So one can also have a higher order analog of this. Instead of a simple pole, you can have a pole of order k. So the statement would look like this. You have, again, the same Dirichlet series, absolutely convergent for real part s greater than 1, and can be analytically continued to real part s greater than equal to 1, except for a pole of order k at s equal to 1 with residue r. So the sum of the coefficients up to x will behave like this residue times upon k minus 1 factorial times x times log x raised to k minus 1. And one has error terms in the literature. Today we will focus on trying to get this kind of error term where you just say one log x. We'll try to do this through a simple method. Okay, so this is the version of the theorem that we will be trying to prove today. And we will be using some basic Fourier, basic properties of Fourier transform and some knowledge about the Lorentz series of G. Okay, these restrictions, like restricting ourselves to non-negative coefficients, this can be dropped. So we can also from this version derive a more general version of the theorem where you allow complex coefficients, and here you have certain conditions. Instead of s equal to 1, I've kept s equal to c here. But again, the same kind of conditions, absolute convergence to the right of 1, let's say, analytic continuation to the right less to greater than equal to 1, except for pole of order k. And these coefficients should satisfy some growth condition. They should be smaller than some bt, where the series corresponding to those real coefficients satisfies the same conditions as the previous. So one can get around these restrictions by doing things like this. And there are, of course, more general theorems in the literature where you can allow more relaxations on your Dirichlet series. Okay, so there are more things one can do. So we will focus on this version of the theorem today and try to look at the proof. So we will use some things about Fourier transform. So suppose f is a compactly supported smooth function on R. We let eta f denote the Fourier transform of f times exponential e to the t. Okay. So we are looking at this representation. So ft e to the t is given by this integral of eta f with this factor e raised to minus iut. Okay. In particular, we are interested in putting instead of t, log t by log x. So in which situation we will be just writing down what we have here. This is the integral that will come up. And since we are in the Schwartz class, we are on smooth compactly supported functions. So the Fourier transform will have rapid decay. So we will be making use of this rapid decay. So it will decay faster than any polynomial growth, polynomial decay. So that's what we have here as the last statement. Okay. And a preliminary lemma that we need is the following. So basically, this follows through interchanging of integrations and all. But okay, let us just define, you can say the jth iterated integral of ft to be this expression on the right side, where we see that you are integrating ft with respect to j many variables with some conditions. So t1 greater than equal to t2, so on. So these conditions are there, and the last variable tj goes from 0 to infinity. And this integral, actually, we can express it in two ways. You can interchange sums, and it's straightforward to actually, we have to get these two identities. So this integral can be expressed in terms of an integral involving the Fourier transform, which is the first equality that you see. And the second equality is an integral involving again the function, okay, where you have condensed all these j many variables into a single variable, and we have 1 by j minus 1 factorial 0 to infinity ft t raised to j minus 1 dt. Okay, so this is our two expressions for this iterated integral, and we will make use of this identity basically in order to go from an integral involving the Fourier transform to an integral involving the function. Okay. So the idea is as follows. We are interested in the sum bt, t goes up to x. But instead of doing that, initially we will look at bt over t, okay? And we will use partial summation to go back to bt. And now this is a standard trick. Instead of going up, looking at bt by t up to x, what we do is we look at an infinite sum and use an indicator, something approximating the indicator function for 1 to x along with it. So, okay, let me just see where it is. So basically this last approximation is the idea. This is done quite often in number theory. So instead of summing bt by t, t going up to x, we will look at bt by t, t going from 1 to infinity with a weight f log t by log x, which will approximate the indicator function of the interval 1 to x, because I'm interested in t going from 1 to x. So how we do this is, this function capital F will be chosen to be a function supported on, on 1 to x, which actually, f will be a function supported on 0 to, well, I want it to be the indicator function of 0 to 1. We will take a function slightly beyond this range, so minus delta to 1 plus delta for some delta. And f of t will be exactly 1 on the interval 0 to 1. So you can see here that when argument is between 0 and 1, that means when you're looking at f of log t by log x, t is between 1 and x. Okay, in that range, f is exactly having the value 1, and it is slightly extending beyond that range also, but it is going to it's going to be like a bump function which decays outside that range. So we can use this approximation, and whatever is extra, we will be putting it into the error terms. Okay, so I hope this is fine. Okay, so we will start with this approximation. This f, in fact, is going to be a smooth function, and it is compactly supported. So this f is the one on which we are going to use our Fourier transform. So we start like this. This left-hand side is the sum that we are looking at as a kind of like an approximation to summation bt by t going up to x. But we know that capital F, I can write this as this integral involving the Fourier transform. So we just plug that in and interchange summation to get what is on the right side of this equality. Now, on this right side, we can justify this integration, the interchange of summation and integration, because we are in the region of absolute convergence. Our s is going to be 1. We are to the right of 1. It is 1 plus 1, 1 plus iu by log x. Okay. Now, our if you look at what is inside this integrand, this is your function, this summation, this series, capital, this is actually g, capital G of 1 plus iu by log x. And the idea is to use now information about the Laurent series of this function, because you do know it has a pole of order k at s equal to 1. So we wish to use this information about the Laurent series of G. There is a pole of order k, so we will have the ck here is the residue. There is a ck upon s raised to k plus a lower order term plus more lower order terms which we are putting in the error. The first two terms we will use. So we want to make use of this, but this is valid when s goes towards 0 from the right side. So we cannot just directly use it here. We have to look at cases where our s actually is going to be in this whole integral, the s will be given by 1 plus iu by log x. So we have to look at cases where s will be going close, will be approaching 0 as x goes to infinity, and where s will not. So we are interested in growing slowly as compared to log x as our first case, and the other case will be the complement region. So the first case will be u is some small power of log x. Let's say we'll just fix some power. This epsilon we'll just keep it as some fixed number between 0 and 1 for now. So in this situation, we can use the Laurent series because s is going towards 0. So now we are looking at contribution to this integral in this region. So what we have done here is, if you look at this first integral, there is a t going from 1 to infinity, bt over something. This is the series. In place of that series, we are going to be using this previous Laurent series expression for g, with s being 1 plus iu by log x. Okay, so if you just exactly substitute, we get this expression. That is, we get the first two terms coming from k and k minus 1 here, and then there is an error term coming from the lower order terms. Okay, so these are this is the expression that we get. Now, this error term, the integral, if you see in this error term, one can actually show that it is absolutely convergent due to the rapid decay of eta f. So one can show that this is big O of 1. So the error term is actually log x raised to k minus 2 that we have here. And we have this first two terms as the main terms, j with k minus 1 and j equal to k. This is what we have for now. Now let's go to the other case where u might be greater than equal to this power of log x. So we look at this second case. Here we cannot directly use the Laurent series expansion. We are outside this, we do not have s going towards 0. But here we can do something else. So we are interested in this series inside our integrand. So we can bound this by, we are using non-negativity of the coefficients at this stage in the proof. We are bounding this by summation bt t raised to 1 plus 1 by log x. And this now is in that region. As x goes towards infinity, s, which is 1 by log x, is going towards 0. So we can use the Laurent series here for this expression. And that tells us, so basically now we are using the Laurent series for g of 1 plus 1 by log x, okay, as x goes to infinity. And that we do not even need the full strength of that. We will just use less than log x, less than 1 by s to the k, which is log x to the k. And we just plug that in. Okay. So when we plug that in, we get our contribution to the same integral now. So we plug that in and we get the contribution less than log x to the k times this integral of eta f in this region. But recall that eta f was having rapid decay. Moreover, in this region, u itself is quite big. So the decay, you can actually make it, you know, how do you say? You can make it smaller than any negative power of log x because of this region that u is in. So in what I want to say is this last statement, basically, eta f is having this kind of a rapid decay, but u is itself bigger than log x. So we can actually play around with the a and make this decay smaller than any power of log x. In particular, we can kill this power of log x, which is out here, this power of log x to the k. We can kill that, and you can even get even more negative powers of log x. So we write that. So eventually, what we are trying to say is that in this case, the contribution to the sum is bounded below any negative power of log x. So that is what we have. So this case does not just gets absorbed into the error term. It does not. It has negligible contribution. Okay. So if we just combine what we have so far, we have obtained two main terms and everything else went into the error term, including the second case. So the error term is log x raised to k minus 1. And we have these first two main terms that we obtained. Now we are still in a situation where the integral is not the full integral. The integral is over the region of the first case, that is u less than log x to some small power. But if so this is also another common trick. What we do is you add the tail and you subtract the tail. You want to make this integral into the full integral. So you add the tail and you subtract the tail, knowing that the tail actually does not contribute much. So you can replace this integral by the full integral, because if you look at the contribution of the tail, this contribution, again, like we did in the previous slide, you can bound it by any negative power of log x. Okay, because here again you use that rapid decay of eta, and you use the fact that u itself is bigger than some power of log x. So yeah, we can just put it in there and we get this first expression with the two main terms involving the whole integral over R, not just this region, not just u less than log x to the epsilon. So let me write that. We have obtained this as our main term. Two main terms here, and we have this error of log x raised to k minus 2. Now the main terms are in terms of an integral involving the Fourier transform. But this is where the our preliminary results come into place. So you recall there was a way of moving from the integral involving the Fourier transform, a specific integral involving the Fourier transform, into an integral involving the actual function, this function f. So we use that. That actually will give us, we use that result. So this integral of eta f now becomes an integral of 0 to infinity of f of t raised to j minus 1. Okay, that is what we have, and there is an extra j minus 1 factorial that comes in the denominator out there. Okay, so we get this. Now, now we have everything we need. F is supposed to approximate the indicator function of the interval 0 to 1, actually. So, and it is something small, slightly beyond that. But if you just think of this f as an indicator function of 0 to 1, then you can actually see what this term will become. So if you look at this integral, it will become an integral of 0 to 1 of t raised to j minus 1 dt, which will then give you 1 by j. So that 1 by j will come out here and combine with the j minus 1 factorial. So this will become a j factorial. So plus we have some little bit extra, which we need to then say it is going to become part of the error. Okay. So for that, we need to choose the support of the function carefully. So it was supposed to be a smooth function supported between, well, we are starting with 0 anyway, but it goes up to 1 plus delta. So this delta has to be chosen small in order to, whatever is that extra contribution, you want to make it negligible. So we choose the delta accordingly. And if we do that, what happens is you can actually see that you get what you want. So even come back here to the left side. This left side, if you put in your indicator function of 0 to 1, you will get exactly summation bt by t going up to x. Okay, so we are choosing our delta appropriately so that everything that is extra can be taken care of in the error term, and we are putting it in terms of whatever we need. So summation bt by t going up to x, and we get these two main terms, that j and j minus 1 factorial combined, and we get j factorial. So this is there's a k factorial here in the denominator and a k minus 1 factorial, and we remain with this error term of log x to the k minus 2. Now we apply partial summation on this sum, and in order we have to do well, kind of a partial summation with some integration by parts, where we need both these terms actually in order to cancel things out. And finally we get summation bt t going up to x will give us this main term, that is the residue ck upon k minus 1 factorial times x log x raised to k minus 1. This is what is prescribed by the Tauberian theorem, and we save a log in our, we have saved a log x in this proof. So this is our simple proof of the Wiener-Ikehara Tauberian theorem. And some concluding remarks that I would like to make is that if you have more information about the Laurent series of G, then you can exploit this to get more main terms. You can get what should be the second main term after this log x, after this x log x raised to k minus 1, and so on. And you can also get better error terms if you have the corresponding information about the Laurent series. So if, for example, if we are able to say something like we know about the first k terms of this Laurent series, and then we have a very good approximation, as in we just have straight away lower order terms starting from some m, s raised to m, as s goes to 0. Then one can obtain a savings of log x raised to m in the error term. More precisely, if you work with the same proof, you can get summation bt by t with these first k main terms and a savings of log x to the m. And if you do your partial summation, you can go back into bt with, again, first k terms coming from some combinations of these with coefficients lambda k's, which are some combinations of these coefficients in the power series, coefficients in the Laurent series, and you have saved a log x raised to m in the error. Okay, so this is what you could get if you have more information about the Laurent series. Okay, so I think I could stop here, and these are some references. Thank you. Yeah.
Thank you, Akshaa. Any questions? Online participants?
I think it's just a question of terminology, Akshaa. On slide 10,
Yeah.
somebody can correct me, slide 10, the definition of a residue, what is the residue? Isn't that usually the coefficient of 1 over s, usually? That's the definition.
Oh, yeah.
So you may want to put s to the k there, or so s to the k minus 1 or something like that there, you know? So
yeah.
ck is the residue of s to the k minus 1 times g of s.
Yes.
Some minor comment, I think. I hope you're feeling better.
Yeah. Yeah, it is cold, so I'm feeling better.
It's just a cold, that's good, okay. Yeah, nice.
What is ck minus 1 in the same formula?
CK minus 1?
Yeah.
So actually, these are just the coefficients coming in the Laurent series. So when you have, so we have a pole of order k at we have a pole of order k at s equal to 1. So the formula will look like it will start from here and there will be lower order terms, right?
So you can't call it residue.
Yeah. This ck minus 1 is not the residue, nor should I call ck also as the residue, actually.
All right. Yeah.
Yeah.
Let's not call it.
All right, let's thank oh, there's another question.
I just wanted to know, if you apply this to the prime number theorem, is there any way that you can push the argument to find an asymptotic formula with the logarithmic integral, or there's no way to go that far?
Oh, you mean asymptotic formula with the logarithmic integral. Okay. So you want to get powers of log x for all savings of all any arbitrary power of log x also. Yeah, maybe. I mean, one would have to write down the power, the series, one would have to write down the Laurent series and do like a very careful computation, maybe. I'm not sure.
One more question, actually.
Yeah, can you remind or recall the original proof of this theorem? Because I mean, I want to see like how simple this is compared with the original one. So like, do you have a sketch or like what's the original proof is like?
So there is an original proof which also uses actually, I don't know which proof is original. I mean, I have seen a proof in Professor Ramurthy's book on analytic number theory. That has a proof using Fourier transform as well, but they use a very specific kernel there for the there's a the choice, they use a specific kernel in their integration. So that choice of the kernel is not intuitive, at least to me, but and that proof is lengthier, I think. But that is the Fourier transform proof that I have seen, and there's also proof probably using Laplace transforms by Korevar that I have seen, but I really don't know what is the original proof. But many of these proofs do not, one thing is that many of these proofs do not try to get error terms. These are asymptotics. So this proof, we are able to get more terms and also an error term. So, and it seems to be shorter.
There's some classical work of Delange in the 50s,
Hmm.
where he uses contour integration, of course,
Yes.
instead of what you're doing. But this is interesting because you are getting these logarithmic terms without contour integration, but by using harmonic analysis, Fourier transforms. But Delange's paper, I think, is considered to be one of the more authoritative versions of the generalized Tauberian theorem. Yeah.
Any more questions? If not, let's thank Akshaa again. And we will resume at 10:45. Thanks, Akshaa.
Thanks, Adia.